Okay, let's start. So today we're going to start chapter 7, where the fun begins. So now we're going to be very integration focused. We're going to learn a lot of new techniques to integrate a lot of interesting functions once we can find something that writes properly. We're going to talk about 7.1. It's going to be called integration by parts. Did you guys talk about this in recitation at all? Or?
Yeah.
Briefly. So we're going to go over it. So back in Calc 1, we learned about what integration was. It was a method of finding the area under a curve. It has all sorts of applications, which in this class you'll see some of them, and in future classes you'll see even more. We also found through the fundamental theorem of calculus that it was the reverse of derivatives in some weak sense. And so pretty much any derivative rule I gave you before can be used as an integral rule in reverse. You just put a plus c on it. So we know about derivatives of basic functions and about integrals of some basic functions. But then we get more complicated functions and then things kind of change. So for example, we know how to integrate something like x squared dx. There's a basic rule for that called the power rule. And then you sometimes end up with something that looks like this. And so you have x squared plus 1 to the 37. And you might not want to expand that and use the power rule, so there's another thing that you can apply, and that was called, in this case, you'd use something called substitution. Now substitution was one of the basic rules. It's just a step above basic. It helps you to deal with very sophisticated cases where you don't have to brute force everything. And what you can kind of do here, so here you would use substitution. Right? In fact, you do u equals x squared plus 1. Right? So what substitution was, this was probably introduced to you, it was you kind of reversing the chain rule. So basically in derivatives, also that was the case, where you had some basic rules that can deal with simple functions, but then when things got more complicated, you had to introduce all these rules. You had to introduce the product rule, and the chain rule, and the quotient rule, and all that stuff. And so what substitution was actually a reverse of the chain rule. And it helps you deal with composite functions, where the goal is to actually replace an expression with a single variable that has with two goals in mind. One, it will make your expression look like a simpler rule. In this case, we're trying to make it look more like u to the 37. And the second thing that you had to worry about is that the variable part of the derivative of this guy, right, in this case the x, was somewhere else as a factor in the function. So you can do a substitution in that case. There are times though when that technique itself is not enough and you need other techniques. And so this brings us to a next technique, which is going to be slightly above integration by substitution in terms of difficulty. It's called integration by parts. And what you want to think of integration by parts as, this is kind of the reverse of the product rule. So substitution was reversing the chain rule. Integration by parts will actually reverse the product rule. So you would actually use this when you want to integrate products. By the way, I will mention that you use it when substitution does not work. And 2, when you want to integrate a product of functions. Now, that word product, we're going to take it very loosely and you're going to see why. But that's basically the idea. So there are times when substitution is not enough. We need something a bit more sophisticated. One of the options is to use integration by parts. So this is when you find yourself in a situation where substitution does not work, but you have a product of functions that you want to integrate. This might work, right? Nothing is ever going to be guaranteed here, but this is going to be one option. Okay? So you might recall what the product rule says. This says if you're differentiating a product of functions, then take the first one times the second, derivative of the first times second plus either the second times derivative of the first. Okay? So this is kind of a loose, I'm not going to be too specific here, but it's a loose justification for the formula I'm going to give you about integration by parts. Right? So we know this rule. So here's the idea. What you do at this point is you integrate both sides. So you're going to go through, you're going to take the integral of this guy, integral of this guy, integral of this guy. And of course, fundamental theorem of calculus tells you that this is going to just be f times g. The integral is going to kill the derivative. Again, kind of loosely speaking here. And then we can kind of end up with this guy, integral of f prime times g, plus the integral of f times g prime. And so, what you do is you kind of solve for one of these guys. Let's say we're going to solve for this guy. So this just becomes the integral of f times g prime is going to be equal to f times g minus the integral of f prime times g. And the goal is here, if you're ever faced with a function where you can conceptualize it in this form, it's one function times the derivative of another function, you will be able to integrate such an expression using this formula. Now, this is not the way the formula is usually written. It's kind of written in a different form, which I'm going to tell you now. If you let u equals your f of x, and you let v equals your g of x, then your du is just going to be your f prime dx, and then your dv is going to be your g prime dx. And so the rule becomes, right, so I'm just going to go into this rule and kind of swap things out. The integral of u dv is u times v minus the integral of v du. Now this is called the integration by parts formula. And so that will be the formula that your textbook tells you you can apply for integration by parts. So this is the integration by parts formula. So let me give you an example, just a quick example of using this formula, and then I'll give you some tips on how to apply this formula for slightly more complicated cases. Then I'll give you another method that kind of puts this method on steroids and gives you even the power of doing a lot more complicated things a lot quicker. So let's jump in with an example. What was my first example? It's not going to be something crazy. Maybe x e to the x was our first example. Integral of x times e to the x. Now there's one thing I want you to note here right off the bat. Is substitution would not work on this guy. Right. For one thing, what would you substitute? Right? U equals x is always a bad substitution, and you literally get back exactly the same thing. You can think of u equals e to the x, but all that would do is transform this guy into an ln x, and we don't even know how to do that either. By the way, we will be able to derive the formula for integration of ln x using integration by parts, by the way. So there's no rule to actually make this guy into a simpler function that we can actually apply a straightforward rule. But I do realize that it's a product of functions. So what I want to do is, I realize that this is a product. So now here's my goal. My goal is to choose one of my functions to be my u, and the other function to be the dv. Okay? So in this case, I'm going to make a choice here. So I'm going to try int by parts. And here's how I'm going to apply my integration by parts formula. Let u equals the x function. Right, so I'm going to let my u equals x. And my dv equals the exponential e to the x dx is going to be my dv. So that's how I'm going to split up this function. I'm going to think of this as a product where this guy is my u, this guy is my dv. And so now I'm just going to find the pieces that I need to plug into this formula. So from my u, I'm going to find the derivative, du. Well, that's just going to be 1 dx. So my du would be dx. For my dv, I need to find the v, which means I'm going to integrate. Integral of e to the x dx is just e to the x. So notice here, I differentiated my u. And I integrated the dv function. Now, plug into the formula. Now the formula says the integral of u dv is going to be u times v minus the integral of v du. There are multitudes of ways you can remember that. I had a friend back when I was in calculus 2. He decided to call this video. He pronounces it in this weird way, so he remembers the last guy's the video, and then all the other guys fell into place. Whatever. I literally actually memorized that as a process. So I just realized that the integral of a product of functions is one function times the integral of another minus the integral of the same function times the derivative of the other. And I can just drop them in. So without actually doing this, I could have just written down an integration by parts without actually writing down the formula. It's because in my head I'm differentiating and integrating while I'm doing it. Whatever way you want to remember it is going to be up to you. You can make up this funny mnemonic and say it weird, or you can say things as a process. But at the end of the day, this is the formula you're going to want to use. And so now I'm actually just going to plug these guys in. So my u is just the x, my dv is the e to the x, so this guy here is the original integral, x e to the x dx. And so now let's actually plug in this side. This is u times v. Here's my u times my v. It's going to be x e to the x minus the integral of my v times my du. Now in this case, you'll notice that v is just e to the x, my du is 1 dx. So this is just going to be e to the x dx. And so now what you've noticed is, through this formula, I've broken down a more complicated integral into a simpler integral. So it turns out I can write this integral as a sum of functions, where one of them happens to be a simpler integral to deal with. Because we do know how to integrate e to the x. So this is going to be x e to the x minus the integral of that is just itself. And so the integral of x e to the x is this function. It's going to be x e to the x minus e to the x. And you can actually check that. You can actually differentiate this, and you realize you get that. So that's just integration by parts. That's one of the basic kind of examples. Before moving on, let's do a slightly more complicated example, which is going to sort of be a justification for a method I'm going to tell you about later on. And then I'll give you some tips. So let's do something slightly more complicated here. What if I had the integral of x squared e to the x? So almost that guy, but just instead now I have an x squared. So again, the first thing I'm going to actually look when I'm faced with any integral that's not just a basic rule is, can I use substitution? Here, notice that substitution does not work. Right? You can try all you want, you're not going to get anything nice enough to actually integrate. Okay? But this is kind of how I do want you to think. Like, faced with a random integral, the first thing I'm going to try, if it's not a basic rule, doesn't work, substitution. It's the easiest one. It's the easiest one to apply. So if it can be applied, you should try to apply it first, and then you kind of move on from there. And so substitution does not work. So I'm going to think of doing integration by parts. Here I'm going to choose my u to be x squared, my dv to be e to the x dx. I'll talk more about making this choice in a bit, but let's actually just run through this. So now my du is going to be 2x dx. My v is going to just be e to the x. And so this would mean so the formula is u times v minus the integral of v du. And I'm just going to be plugging those in. So my u is x squared times v e to the x minus the integral of my v times du. And so now you might have seen there's an issue. It's not insurmountable, but it is currently an issue. The integral that you get as a result is not straightforward itself. Notice that that integral is actually similar to this integral. It gives us back an x e to the x. So I am in a simpler situation. I don't have x squared e to the x, but now I have x e to the x. So what do I do there? Do integration by parts again. Right, so I'm going to go here, and I'm going to do another u equals 2x. And my dv equals e to the x dx. And so then my du is equal to 2 dx. And so my v is equal to e to the x. And so I'm going to go back from the beginning. That's x squared times e to the x minus, now in parentheses, I'm going to apply the integration by parts formula again. Yeah?
Would it be easier to pull out the 2 if I integral first?
And I would just put it here.
Yeah.
In this case, it's personal preference. I don't see that as making it significantly easier. If psychologically for you it is easier at some point, there's no harm in doing that. But to me, dealing with a 2x is not that big a deal. But I could, yes, pull this out, put the 2 here, and then do integration by parts on the x e to the x, in which case exactly this would have happened in the parentheses. So I put my u times my v minus the integral of my v du. So I apply that formula again. This time inside parentheses. So now I have my x squared e to the x minus 2x e to the x. Okay, put out that plus the other side there. And so here I have x squared e to the x minus 2x e to the x plus 2 e to the x plus c. Or, which is fine for me, or you could actually write that as something like x squared minus 2x plus 2 all times e to the x plus c. But this example, But this example actually illustrates a point. Sometimes you might have to do integration by parts repeatedly, and you can already kind of see that that's kind of can get annoying if you have to do it multiple times. For example, this were an x cubed or an x to the fourth. Let's do it 4 times in a row, and you'd have parentheses within parentheses, and it can get kind of tedious. I'll teach you a workaround for that, but you get the idea. So the important idea is, one, substitution would not work, which is always going to be one of the first things you look for. And then once you realize it's just a multiplication of functions, that's going to be loosely defined, so you can try integration by parts, in which case you're going to choose one of your functions to be a u, the other function to be a dv, differentiate the u, integrate the v, plug into that formula. The hope is you'll end up with another integral that's easier to deal with, which that integral itself you might have to break down using integration by parts, but it should be something that's easier to deal with. It's worth mentioning here that had I chosen my functions the other way, things wouldn't have worked out that nicely, right? If I had chosen the u to be the e to the x, and my dv to be the x squared, what would have happened? I would have integrated and gotten an x cubed. And then the guy here would end up being an x cubed e to the x, which is kind of more complicated than that guy. I would have gone in the wrong direction, right? So while the method itself isn't that bad once you can make the choice, making the right choice in the first place is actually something that's very important, because you can end up with something more complicated if you make the wrong choice. So let's talk about how to make the right choice. So who you choose to be u versus dv is important. The wrong choice can give you something more complicated. Here's how to choose. The rule is specifically focused on the u. Here's how to choose your u. And hence, once you know who your u is, you'll automatically know the other guy is going to be the dv. But this is a mnemonic that focuses on the u. So there's a mnemonic. It's called liate. Okay. Which you kind of memorize that in a kind of vertical step ladder, where people at the top of the ladder get to be u first. And it goes down, gets to be u last. Now these letters in liate, they actually stand for something. The L stands for logarithms. The I stands for inverse trig functions. The A stands for, because if we had like a P here, it would be, it wouldn't actually flow very nice. So it stands for like algebra, but really you want to think of this as polynomials. The T stands for good old-fashioned trig functions, not inverse trig functions, but regular trig functions. And the E stands for exponential functions. So basically the idea is the following. If you have a couple of these functions being multiplied together, you choose the u based on the kind of function you're looking at. So in this example, for instance, when you had that x squared e to the x, notice that this function fell in the category of a, while this function fell in the category of e, right? So according to my liate rule, a is higher than e, the a function gets to be the u, right? So I would choose this guy to be u. Right? Because it's higher in the ladder than the exponential function. So if you have a product of functions, what you do is you look at the kinds of functions that show up, and based on where they fall in this ladder, you would choose one to be the u over the other one. And that will always end up in a simpler way. Right? So you can kind of see that if you have an algebra and an exponential, choosing this guy to be the u, you differentiate him, you keep breaking down the polynomial till it eventually becomes nothing, right? Whereas if you went the other way, that wouldn't have happened, right? If you had a log and this guy gets to be the u because you can break a log down into 1 over x, which is going to, the polynomial will end up killing that x usually, right? So it's a very nice way of choosing your u in a very efficient way. Okay. So that's how you actually make the choice of who gets to be your u and who gets to be your dv. So that's kind of like in substitution when you had that rule. How do you choose who to be the u? Well, you choose it so that the function gets simplified and the derivative of the thing that is the u is somewhere else in the function. So if you want to apply integration by parts, how do you choose your u? You choose it according to this step line. Yeah.
What do you mean by like the polynomial would kill the derivative? Would that like they would cancel?
Yeah.
Okay.
In fact, I think I have an example of that. Let's do an example where I'm talking about the L versus the A. So let's say I had something like the integral of x squared ln x. So what you do is, again, notice substitution won't work. And so then you think into by parts. Then you realize this guy here is an A, this guy here is an L. So that tells you that your U must be the ln. Because of Leate. L is higher in that ladder than the A. Your dv will just be the x squared dx. The other function gets to be your dv. So your U is this because of Leate. So then your du ends up being 1 over x dx. Your v ends up being x cubed over 3, right? Which at first glance you might freak out thinking that the power is going to get higher, but don't remember, in that formula you're going to multiply the v into du. So that's going to kill that x, right? So it's not actually getting worse, right? In fact, in the integral part, you won't have ln's at all. And so now I can actually go with this integral. So this is x squared ln x dx. And that's going to be u times v minus the integral of v times du. So you see this integral here is actually now not so bad. I can simplify that. And so this ends up being x cubed over 3 ln x minus, well, a third times integral of x squared. So I can integrate x cubed over 3 ln x minus, to integrate the x squared, that's x cubed over 3, so this just becomes x cubed over 9. Yes?
Just double checking that we'll never have two of the same letter? Like you'll never have two A's or like two L's or something?
Yeah, because normally you'll be able to combine them if that's the case.
Right.
If I have a polynomial times another polynomial, I can just multiply out and get another polynomial.
Okay.
Or something similar would happen. Right? Or, yeah. But there are weird cases that can happen. For example, there are times when you might only see one function, but it turns out that the correct way to approach it is integration by parts. So you might have realized, of course, well, I don't know if it kept you up at nights, but you might have realized that we do know how to integrate e to the x, but we don't know how to integrate ln x, right? Which is a very basic function. You'd think that we know how to integrate that. Well, we do, and now I'm going to show you how. So let's say you wanted to integrate just ln x by itself. What's the integral of ln x? So a knee-jerk reaction might be to say 1 over x, but remember that's the derivative of ln x, that's not the integral of ln x. How do you actually integrate that function? Right? So here's the trick, if you can call it that. The trick is to think of it as being 1 times ln x. And so now you've introduced 2 functions technically. 1 would fall under a because it's a polynomial, and then the ln x will fall under the L, which is a logarithm. So my ln x is going to get to be my u, and the function 1 dx is going to be my dv. So here I would set u equals ln x. We do know how to differentiate ln x, so that's not a problem. So this would mean my du is equal to 1 over x dx. And so my dv would actually be 1 dx. And so my v is actually going to be x. So this is what I meant by the word product can be interpreted loosely. Sometimes you can invent a product when it's not there by just taking one of the guys to be 1. And then think of it as a product of 1 times the function. And so now, when we start to plug into that formula, it's going to be u times v, x ln x, minus the integral of v times du. Of course, this guy cancels. So that just becomes x ln x minus the integral of 1 dx. And the integral of 1 we know is x, so this becomes x ln x minus x. Which, by the way, at this point, this is now a rule that we know now. We know this now. It's just something that we should have memorized. The integral of ln x is x ln x minus x. And it is derived using integration by parts. Do a couple more examples. This one is just another example like that guy. Then I'll give you another example which was going to motivate the need for a technique that I'll probably obviously have to show you next class, but I don't know if I'll have enough time to show you this class. So something like sine inverse of x. How do you differentiate an inverse trig function? Trick is going to be similar to this, right? So think of this as 1 times sine inverse of x. That's my a. This guy is going to be my I. In Liate, the i's come first. It's going to be u is equal to sine inverse of x. What's the derivative of sine inverse?
1 over square root of 1 minus x squared.
So my dv here is going to be 1 dx. So my v is going to be x. So I can start to plug this in. So my integral of sine inverse of x dx is going to be equal to u times v minus the integral of v times du. Now how do you do with this guy? Substitution. Right? So this is illustrating the point that sometimes you'll need several techniques to deal with an integral. So here, I would actually use substitution to deal with that guy. So I can do something like u squared is equal to 1 minus x squared. So 2u du is equal to minus 2x dx. So u du is equal to x dx. And so this guy would be x sine inverse of x minus the integral of my x dx is now minus u du. This guy is now u. So that just cancels. So this becomes x sine inverse of x minus integral of, or plus integral of 1 du. X sine inverse of x plus u c x sine inverse of x plus, and my u is actually just the square root of 1 minus x squared. So this is going to be integral of sine inverse of x dx. That's not something you have to memorize, I'm just rewriting it. Yes?
Why'd you do u squared as 1 minus x squared?
Oh, I'm doing a substitution, so I just did u squared substitution.
Okay.
It's just kind of to avoid the annoyance, I mean, of having that radical there. So probably a typical thing you would have done is just u equals 1 minus x squared. So your du would be minus 2x dx. So you have minus a half du is equal to x dx. And so this integral would end up being minus a half times 1 over the radical of u du. Right, so it's just a trick to avoid having a radical after you do a substitution, is to actually put the radical in your substitution. So instead, I did u equals that whole radical. So I can replace the entire denominator by u, but that would mean that u squared is 1 minus x squared, and then we'll differentiate both sides implicitly, and we can continue with that. There are many cases in which thinking of things in that term, you don't literally have to substitute a u for something. You can substitute a u squared, or substitute a u cubed, or you can substitute anything that's convenient. The goal, remember, is just to simplify the function as much as possible. And its derivative must be somewhere else in the function. So when I took that derivative, I got an x, and there's an x. So you can really substitute anything. But yeah, I kind of glossed over that. You may or may not have seen that kind of modification on substitution in Calc 1. When I taught Calc 1, I told my class about it, but I don't think when I took Calc 1, my professor told us things like that. So yeah, you can get away from just substituting a u. You can actually substitute something that makes it even simpler. So if there was a cube root here, I probably would even substitute a u cubed. Let's see, what else can we do? So, let's look at this example. Something like e to the x, I think I did sine x or cosine x. It's going to be the same thing either way, whether I put a sine x or cosine x. So you look at something like that. You realize substitution won't work, and so you kind of want to do integration by parts. And you're going to come into a hiccup here, but on Friday we'll learn how to deal with that hiccup in a very nice way. And so one thing you're going to do here is recognize that that's going to be an e. This guy here is going to be a t. So in terms of layout, we should choose the trig function as our u. So let's actually go through with that. U equals cosine, my dv is equal to e to the x dx. So my du is the derivative of cosine, which is minus sine, and my v is going to be e to the x. And so I'm going to plug that in. U times v minus the integral of v times du. That becomes a plus. And so you end up in this situation. And then you realize, you know what, e to the x sine x is actually pretty similar to e to the x cosine x. I'm now in a situation where I have to do integration by parts again. And so you go, okay, let's do it again. So you come over here, and you let u equals sine x. Your dv equals e to the x. So your du is going to be cosine x. And your v is going to be e to the x. And so let's actually try this one more time. So we have e to the x cosine x plus, parentheses, u times v minus the integral of v du, e to the x cosine x. For a moment you're like, wait a tick. Now I ended up with the same guy back again. Like, what do I do? Integration by parts again? No, eventually I'll come to a point where I get the same guy back again. And it seems like the process is broken. Okay, integration by parts is useless now once I get something like moderately complicated. It turns out that it isn't that bad. So at this point, if you're doing integration by parts and you get the same guy as the original, what you do here to deal with this is you stop and use algebra. You basically solve for that guy, right? So basically, so notice here if I set I equals this integral that I'm after, then what I actually have here is I is equal to e to the x cosine x plus e to the x sine x minus I, right? So now it's really an algebra problem. Let's just solve for the guy that we want. So this would just mean that 2i is equal to e to the x cosine x plus e to the x sine x. And so my I is just 1/2 times all of that. Of course, there should always be a plus c. Right, so this is kind of like a revolving integration by parts. It's not really a repeating integration by parts. So it revolved on itself. You end up by going through the integration by parts formula, the original integral shows up somewhere else. If that happens, at that point all you do is you just stop and you just bring that integral to the other side. And so that's how you would integrate this guy. That would be the answer here. So in terms of what your textbook did, there's really nothing else to tell you. But I'm going to give you another method that can kind of put this method on steroids. It'll deal with all these nuances, and you can kind of figure out a quick way through them. We'll talk about that on Friday. And also start talking about trig integrals. Some more trig integrals, some more complicated terms. So we'll stop there. I'll see you guys on Friday.
For the exam, you said you would put like a mock exam on the website.